Hey there. Ever wonder how we know if an AI is being fair? Like, say, when a hiring tool decides who gets a job, or a loan app determines creditworthiness. It's not as simple as checking if everyone gets the same result. Today, we're diving into a game-changing approach to AI fairness, one that tackles a sneaky problem: sample size. Let's start with the basics. Traditionally, fairness in algorithms has been checked using simple rules like saying, if a group's approval rate is below 80% of the overall rate, it's unfair. But here's the twist. This method ignores something huge: how many people are in each group. Imagine two groups, one with 10,000 people and another with just 10. A tiny difference in approval rates might look unfair in the small group, but it could just be random luck. The old way treats both the same, which is, well, not great. And it gets trickier with intersectional groups, like someone who's both a woman and a member of a minority ethnic group. These subgroups are often super small, which means the data we have about them is sparse. Think of it like trying to guess the average height of a group when you've only measured one person. The results are all over the place. Current fairness checks can't handle this, leading to false alarms or missing real issues. So how do we fix this? Researchers came up with a smarter framework that adapts to group size, using statistical hypothesis testing instead of one-size-fits-all rules. It's like giving the algorithm a built-in uncertainty meter that adjusts based on how much data you have. Here's the clever part: they use two methods depending on the group. For larger groups, they rely on the Wald test, which uses math to calculate confidence intervals. Think of it as a margin of error. If a disparity falls outside this range, it's likely real, not random. For smaller groups where traditional methods fail, they switch to Bayesian inference. This is like using a flexible model that learns from limited data, getting better as more info comes in. But here's where it gets even wilder. The delta method is like a superpower that lets us stretch or shrink that bell curve. Why? Because some fairness metrics, like checking if a model treats men and women equally, are more sensitive to changes in data than others. If you tweak the data a little, how much does the fairness score jump? The delta method answers that, letting us predict how wobbly our measurements might be. Now here's the real-world test. Researchers applied these tools to datasets like German credit, which tracks loan applicants, and student performance, which looks at grades. They trained a model called XGBoost, a data sorting machine that's way faster than your average spreadsheet, to spot fairness issues. But here's the twist. Traditional methods used fixed thresholds, like saying, if the fairness score is below 0.8, it's biased. But wait, what if the group being tested is tiny? Imagine analyzing a subgroup of just 10 people. A few bad outcomes could make the model look unfair, even if it's not. That's where the new approach shines. Instead of rigid rules, it uses confidence intervals, like a margin of error for fairness metrics. For large groups, the Wald test gives precise bounds. For small ones, Bayesian methods inject prior knowledge to stabilize estimates. This isn't just theory. When applied to real data, the framework caught biases that old methods missed, like subtle disparities in loan approvals for underrepresented groups. It's a huge leap forward because it balances rigor with realism, acknowledging that some groups will always have less data. So next time you hear about AI fairness, remember, it's not just about equal outcomes. It's about how we measure those outcomes, accounting for the messy, imperfect world we live in. And that's where this research shines, turning statistical nuance into actionable insight. Thanks for watching. If you want to dive deeper into the math or see how this applies to specific models, hit subscribe and let me know. The future of AI fairness is being written, and you're invited to the lab.